Okay, hello and welcome back. In this video, we're covering section 7.1 on the inverse, sine, cosine, and tangent functions. So we've been spending a lot of time working with trigonometric functions and their properties, and we'll also see that these functions have inverses with specific properties as well. So I want to first go over a few attributes of inverse functions, just as a brief review. So we can say if f of x and f inverse of x, so the little notation for an inverse function, looks like a negative 1 power, but in function notation that means the inverse. So if these are inverse functions, we can say a few things. One is that they trade domains and ranges. So I can say the domain of f is the range of f inverse. And then we can say the range of f is the domain of f inverse. So they swap domains and ranges, they swap their inputs and outputs. And then we can also say if we were to plug one into the other, if we find f of f inverse of x, meaning we take an inverse function and plug it into the original function, they undo each other and you just get the argument out. You just get that original input. And we can go the other way too. We can take the inverse function and plug in the other. They will also undo each other. And you just get the argument back. So you've probably seen this with the logarithmic function and the exponential function. They have these properties. So the trigonometric functions also have inverses, but under specific conditions. Um, if you remember, for a function to have an inverse, for it to be invertible, it needs to be 1-to-1. Meaning that each input is paired with exactly one output. Visually, we can use what's called the horizontal line test. So it must pass the horizontal line test. Meaning if we were to have some function and we draw a horizontal line, it needs to only hit the function in one place, in one location. So let's keep that in mind. So in our case, if we have something like the sine of x equals y, the trig functions take some angle as an input. You can say the domain is a set of angles and it produces some value as an output. I'm just going to say value. So if we have the inverse sine, which we'll define in a moment, so the notation would be like this, using this inverse notation. Let's actually swap x and y here, just to show this swapping of inputs and outputs. The inverse sine, and in general the inverse trig functions, take in some value as the input. So it's like a trigonometric value, like a location on the unit circle, and it produces an angle as the output. So we swap inputs and outputs between inverse functions. So let's keep some of these properties in mind and start to define what some of these inverse trig functions are. And we'll start with the sine. So I mentioned that it must be one-to-one or pass the horizontal line test in order to be invertible, in order for us to say that it has an inverse. So let's imagine the graph of the sine wave. And I'm going to do a period in the positive direction, so out to 2 pi. And let's also look at it backwards to negative 2 pi. So this would be negative pi over 2, and negative 3 pi over 2. And the amplitude is amplitude is 1, so it'll be between positive 1 and we'll call this negative 1 down here. Let me scoot this up a little bit. All right, so let's build a sine wave. So sine starts at the middle point, then up to a maximum, down back to middle, down to its minimum, back up to 0 at 2 pi, and then onward from there. And then we can play this pattern in reverse, thinking about a period in the opposite direction. So this would be going forward. And we can go the other way. So this is just 2 periods of the sine wave, but it can continue on infinitely in both directions. And so if we were to draw a horizontal line, it would fail the horizontal line test in infinitely many points. It's going to keep hitting the sine wave. So that means we can't take the entire sine function and invert it, but we can restrict the domain. We can just take a slice of this function in order to produce a subset that is invertible. And so there's different areas that we can slice the domain, but typically we take this interval between negative pi over 2 and pi over 2. Let's imagine this subsection here. And so notice now, if I were to draw a horizontal line anywhere inside of here, it would only hit the function in one location. So it's one-to-one within this restricted interval. So this is from negative pi over 2 to pi over 2. So that's what they have as their definition here. So we can say we have our inverse sine function where we are bound between negative pi over 2 and positive pi over 2. So let's list out some of these attributes. And we'll compare it to the original sine function. So we can say the sine of x, and then let's compare it to the inverse sine. So the sine function has a domain normally from negative infinity to positive infinity, but we're saying we're going to restrict it from negative pi over 2 to pi over 2. And the range is from negative 1 to positive 1. That's the range of the sine function. And we could have a few points. So let's work on imagining what the graph would look like. So let's take x and then the output being the sine of x. So take a few points like negative pi over 2. The sine of negative pi over 2 is negative 1. The sine of 0 is 0. And the sine of positive pi over 2 is up at positive 1. So let me scoot this over, and let's compare this to the inverse sine. So we mentioned that inverse functions swap domains and ranges. So the domain of the inverse sine will be between negative 1 and positive 1. And the range is between negative pi over 2 and positive pi over 2. So we're swapping the domains and ranges. So let's also build a similar table of values. And since we're swapping domain and range, we can think about just swapping these coordinate points. So instead of negative pi over 2, negative 1, like we have for the sine, we can say that would take an input value of negative 1 and produce negative pi over 2. We'd still have the point 0, 0, because that's just swapping 0 for 0. And then when x is equal to positive 1, it would produce the angle pi over 2. So let's do a quick sketch of what this graph will look like. So we're going to be between negative 1 and positive 1 on the x-axis, and now the y-axis will be our angle. So this will be positive pi over 2 up here and negative pi over 2. So we should have the point negative 1, negative pi over 2, so down here, the point 0, 0, and the point positive 1, positive pi over 2. And the graph will have a smooth curve looking something like this. So this will be the graph of the inverse sine function. So the important thing right now to keep in mind is this restricted range of the sine function. It's restricted between, and I use these little diagrams. So we're just on the right side of the unit circle, to think about it that way. We are between negative pi over 2 and positive pi over 2. Those are the only output values that we will get from the inverse sine function. So this little diagram can be helpful. So let's try solving a few questions using the inverse sine. So let's find some values. So the thing to keep in mind, which I'll write again up here, is the range of the inverse sine is between negative pi over 2 and pi over 2. So I'll draw that little diagram again. So we're on this right side of the unit circle. So that means the inverse sine will only produce output values in this range. So let's look at a couple examples and see why this is important to remember. The first one is asking for the exact value of the inverse sine of positive 1. So we can say this is equal to something. Let's say this is equal to y. So we can view this as asking, we have 1 as an input, and we said earlier the output of the inverse trig functions are angles. So we can view this as asking what angle in that restricted range, so in this interval from negative pi over 2 to pi over 2, will give a sine value of positive 1. And we can also do this a little bit more analytically by taking the sine of both sides. We can see that same kind of statement. If I take the sine of the left side and the sine of the right side, here we have an inverse function plugged into the original function. They're going to undo each other and we'll just get what is inside, just that 1. So they'll cancel. Get 1 equals the sine of y. We can ask what is this value? What angle will produce a sine value of 1? So just another way of looking at that. Can probably already think of this, but it's helpful to remember our reduced range. It needs to be in this interval from negative pi over 2 to pi over 2. And the sine is equal to 1 up here at positive pi over 2. That's the coordinate point 0, 1. So I can say y must be equal to pi over 2. So that's what our original statement. Since this is y, this is what we said was equal to the inverse sine of 1. So inverse sine of 1 is equal to pi over 2. The angle that produces a sine value of 1 is pi over 2. And that one was pretty simple because there's actually only one point on the unit circle that has a sine value of positive 1. Let's look at one where that's not the case. So this one is asking for the inverse sine of negative 1/2. So I'm going to do a similar thing. I'll say this is equal to something, equal to y. I can take the sine of both sides, and then they'll cancel on the left side. So I get this statement, negative 1/2 equals the sine of some angle. So I'm thinking in that restricted interval, so between negative pi over 2 and pi over 2, where's the sine equal to negative 1/2? Well, it must be down here in the fourth quadrant, since sine is the y part of a coordinate point on the unit circle. So sine is equal to negative 1/2. That will be down here at negative pi over 6. That has the coordinate point positive root 3 over 2, negative 1/2. And there's our sine value of negative 1/2. So notice we have to express it as this negative angle because that's our restricted range. So we couldn't say 11 pi over 6. Even though it's coterminal, we have to give an output in this specific range of values. And there is another angle on the unit circle. We could imagine at 7 pi over 6. The sine is also negative 1/2, but again, it's outside of that range, that allowable set of output values. So we take this single value here. So I can say this angle is negative pi over 6. So our original statement, the inverse sine of negative 1/2 is equal to negative pi over 6. That's the angle that produces a sine value of negative 1/2. So we're kind of thinking backwards. We're pretty used to being given an angle and asked what is some trig value of that angle. Now we're given a value and we think about the angle that produced that value. So thinking a bit backwards. So let's take a look at the inverse cosine. This will be a similar setup. We need to find some restricted domain of the cosine that will allow it to be invertible, that will allow it to pass the horizontal line test. For the cosine, we can just look at a single period, let's say from 0 to 2 pi. Amplitude of the cosine is 1. Cosine starts at its maximum, then down to a middle point, down to a minimum, back to the middle, and completes the cycle at its maximum. Kind of a rough cosine here, but that's okay. So similarly, and this continues in both directions, and it fails the horizontal line test infinitely many times. We could also slice this up in many different ways, but the common reduced domain is from 0 to pi. If you look at it just in this interval, then it will pass the horizontal line test. This is from 0 to pi. So that will be our restricted domain of the sine function, and thus that will produce our restricted range of the inverse cosine. I think I just said sine, I meant to say cosine there. So let's do a similar thing. Let's try to build the graph. So we have the cosine. We said we're restricting the domain to this interval between 0 and pi. And the range of the cosine is between -1 and +1. Can build a few values. So cosine of 0 is +1. Let's put pi over 2 in the middle here. Cosine of pi over 2 is 0. And the cosine of pi is -1. So let's use those 3 points. So let's consider the inverse cosine. This will have a domain between -1 and +1. And the range will be between 0 and pi. That's our range of allowed output values. Let's build a few points here. And let's just swap them like we did with the sine. So instead of 0, 1, we should have the point 1, 0. Instead of pi over 2, 0, we should have 0, pi over 2. And instead of pi -1, we should have -1 pi. So let's plot these and see. So x is between -1 and +1. That will be our domain. And then the range is going from 0 to pi. So let's place pi over 2 in the middle here. So we have the point -1 pi. So start up here. We have the point 0 pi over 2 and the point +1, 0. And we get another smooth curve in between. And this will be our inverse cosine. So between -1 and 1 as the restricted input, and between 0 and pi for our output. So let's look at a few similar questions involving the inverse cosine. So here we will consider the range of inverse cosine is between 0 and pi. So this one I can imagine just the top half of the unit circle. That's where all of our outputs will exist. So the inverse cosine will only produce outputs in this range. So let's look at a few examples. The first one is the inverse cosine of 0. So what angle produces a cosine value of 0? And we can also take the cosine of both sides and get a similar kind of statement. So 0 equals the cosine of some angle. Well, on our restricted range, we're between 0 and pi. The point that has a cosine of 0 will be here in the middle at pi over 2. That's that coordinate point again, 0, 1. It has a cosine value of 0. So that's what our statement should be equal to. You can say y equals pi over 2. So therefore, the inverse cosine of 0 equals pi over 2. That's the angle that produces a cosine value of 0. Okay, let's look at one more for the inverse cosine. That was another easy one because the cosine is equal to 0 only at one point on the, or no, at 2 points actually. Yeah, so there was another point down here at 3 pi over 2. We would get another cosine value of 0. However, we can only give an answer within this restricted range. That's why we keep bringing that up. So let's look at this second example. We have the inverse cosine of negative root 2 over 2. So I can say this is equal to something, some angle. I can take the cosine of both sides. Let's just jump to where it will cancel on the left side. So negative root 2 over 2 equals the cosine of some angle. And I'll remind myself it needs to be between 0 and pi. So negative root 2 over 2, that means we should be in the second quadrant. It's where the cosine is negative. And root 2 over 2 happens at the pi over 4 angles. So that 45-degree angle in the second quadrant is 3 pi over 4. That has the coordinate point negative root 2 over 2, positive root 2 over 2, with the cosine being the x part of that coordinate point. So we can say the angle we're looking for is 3 pi over 4. So the inverse cosine of negative root 2 over 2 equals 3 pi over 4. That's the angle that produces a cosine of negative root 2 over 2 in this restricted interval. And just like our last one, there is a second angle in the third quadrant that has a negative root 2 over 2 cosine, but it's not in our restricted range. So you have to choose the one that's in the bounds that we're working in. All right, and then let's look at the tangent. So how does the tangent need to be restricted? If we remember the graph of the tangent, we have a bunch of vertical asymptotes at odd multiples of pi over 2. So we can imagine over here, negative pi over 2. Over here at positive pi over 2, we have some vertical asymptotes. And then in between, remember the tangent function kind of looks like a cubic function. Let's call this pi over 4, negative pi over 4, and then positive 1 and negative 1. So the tangent is increasing, goes through the origin. At pi over 4, it's equal to 1. So we get this semi-cubic behavior that's bound between the asymptotes. Not the best tangent here. We can get the idea. And this continues, so we would have another copy on both sides. So all we really need to do is just take one period of the tangent function, because it already is one-to-one in between these asymptotes. Anywhere we draw a horizontal line, it will only cross the graph at one point. So let's say our restricted domain of the tangent will be between negative pi over 2 and pi over 2. But this time we won't include the endpoints because the tangent is undefined there. Those are vertical asymptotes. So it's similar to the inverse sine. Remember that was also bounds between negative pi over 2 and pi over 2, but this time we won't include those two endpoints. So let's imagine the graph. Let's do another similar analysis. So let's start with the tangent. We are restricting the domain to be between negative pi over 2 and pi over 2, not including the endpoints. And then the range is negative infinity to positive infinity. Continues in both directions. Let's build a couple values we can work with. So we know at negative pi over 2, the tangent is undefined. At negative pi over 4, the tangent should be negative 1. At 0, the tangent is 0. At positive pi over 4, we get a positive 1. And then at pi over 2, we get another vertical asymptote, so I'll say undefined. So how will this transfer to the inverse tangent? Well, the domain and range will swap, so this time we'll have a range, or let's start with the domain. We'll have a domain that's between negative infinity and positive infinity. And then the range will be restricted between negative pi over 2 and positive pi over 2, not including the endpoints. And then let's get a couple values here. So now we're going to have some horizontal asymptotes. We can say x is undefined when the output is negative pi over 2. Then we should have the point negative 1, negative pi over 4. So again, just swapping our x and y columns here. We'll have the point 0, 0. We should have the point positive 1, positive pi over 4. And then another horizontal asymptote, so x will be undefined whenever y is equal to pi over 2. So we're swapping vertical asymptotes for horizontal asymptotes. Let's do a quick little sketch. So up here at positive pi over 2 and negative pi over 2, I have some horizontal asymptote. So the range is bound between these. And let's have -1 and +1 here. So that'll be positive pi over 4, negative pi over 4 on the y-axis. So we should have the point -1, negative pi over 4. So down here, 0, 0, and then +1, positive pi over 4. And then it will approach the asymptote on the top and the bottom. So this is our graph of the inverse tangent. And just like with the sine and cosine, let's look at finding a few values using this. So we want to remember that the range of the inverse tangent is between negative pi over 2 to pi over 2. So similar to the cosine, except it can't be pi over 2 or negative pi over 2. That's where our asymptotes were. So I can do a similar sketch, but I'm going to put little open circles here just to show that we're not including negative pi over 2 or pi over 2. So our function, the inverse tangent, will only produce output values in this range, so the right side of the unit circle. So let's practice with a couple examples. First one is asking for the inverse tangent of 1. So that's equal to something. We can take the tangent of both sides. This step isn't fully necessary if we just think, okay, what angle produces a tangent value of 1? But it can be helpful to show it in this way, especially when things get a little more complicated. This practice can be useful. So 1 equals the tangent of some angle, and I want to think specifically on the right side of the unit circle. Well, that should be in the first quadrant because it's positive, and pi over 4 has the same x and y value, root 2 over 2, root 2 over 2. So the tangent, since it's sine over cosine, tangent of pi over 4 will be +1. So that's what our angle should be. So then I'll say that's what the inverse tangent, +1, is equal to pi over 4. All right, let's look at the second one. So we're asked for the inverse tangent of negative root 3. That's equal to some angle. Take the tangent of both sides. Let's just skip to negative root 3 equals the tangent of something. This can be a little bit more tricky if you don't have tangent values memorized. I usually think in terms of sine and cosine. So something divided by something in terms of points on the unit circle equals negative root 3. And I know I have values like root 3 over 2, 1/2. I want to keep the root 3, so it's most likely root 3 over 2, let's take the negative root 3 over 2 divided by 1/2, because that would flip the 1/2 into a multiplication, reduce the 2's, and that would give us negative root 3. So I'm looking for the coordinate point where since tangent is sine over cosine, the cosine is 1/2 and the sine is negative root 3 over 2. So we are in this restricted range. On the right side of the unit circle, positive 1/2, negative root 3 over 2. We have to describe it as a negative angle because this is negative pi over 2 down here. So this should be negative pi over 3 that has that coordinate point. So that's what our angle should be, negative root 3, or negative pi over 3, I mean. So I can say the inverse tangent of negative root 3 equals negative pi over 3. So we just need to be really careful about which value we choose as the output because of these restricted ranges of the inverse sine, cosine, and tangent. All right, let's continue with a few more examples. So we're going to use properties of inverse functions to find the exact values of certain composite functions. So functions plugged into inverse functions or vice versa. And they're mentioning here that restricted range of the inverse sine function. So let's look at this first one. And I'll write this again. We need to be between negative pi over 2 and pi over 2. That's the range of inverse sine of x. So the first example is asking us for the inverse sine of the sine of pi over 8. So if I have something like this, I think about where this angle will be. Well, this angle pi over 8, it's half of pi over 4. So it's like somewhere up there in the first quadrant. So it's definitely in between negative pi over 2 and positive pi over 2. So that means that these are just going to undo each other. I can say the inverse sine of the sine of pi over 8 should just equal pi over 8. Because this will give you some value. The sine of pi over 8 will give you some value. And then when I take the inverse sine of this value, it will just give me an angle back. And that angle, we've confirmed, is within the range of the inverse sine function. Let's look at a converse example where that's not true. So in part B, we have the inverse sine of the sine of 5 pi over 8. And it's tempting because we've been saying that these will just undo each other and give the angle out. But we have to keep this restricted range in mind. So is 5 pi over 8 outside of this restricted range between negative pi over 2 and pi over 2? Let's think. Let's convert the pi over 2 to something in eighths, just to reference. Pi over 2 is 4 pi over 8. So since we have 5 pi over 8, that's definitely outside of this restricted range of the inverse sine. Yeah, 5 pi over 8 will be over here, somewhere in the second quadrant. Let's say somewhere out here. And we're dealing with the sine, so we want to find some equivalent angle in the first quadrant, because we want to be between negative pi over 2 and pi over 2. There's some equivalent angle in the first quadrant that has the same sine value, because they're on the same horizontal line. So what can we do? Well, if we subtract pi over 2, so pi over 2 is this 90 degrees here, and pi over 8 goes beyond 90 degrees into the second quadrant. If we subtract pi over 2 from 5 pi over 8, we'll get just this inner angle here. So let's find out what that angle is. If I have 5 pi over 8 and I subtract pi over 2, which we can write as 4 pi over 8, we'll get 1 pi over 8. So let's take that same amount, this is a pi over 8 angle, and subtract it from pi over 2, and that will tell us what this angle is here. So instead of pi over 2, I'll say 4 pi over 8 again. And then let's subtract that angle of pi over 8. That gives us 3 pi over 8. This will be this angle in the first quadrant that will have the same sine value. So I got to say the inverse sine of the sine of 5 pi over 8 will be 3 pi over 8. So we're not able to just pull the angle out. We have to get something that has an equivalent sine value within our restricted range. So it's a little bit tricky. So if you see a statement like this where it's a trig function or the inverse of a trig function with the original trig function inside, before just taking what's inside, we have to make sure that we are in our restricted range. Let's look at a couple other examples. So in example 8, we have the sine of the inverse sine of 0.5. So notice this time the inverse function is inside. And the inverse sine has a restricted domain. Make a little space here. It has a restricted domain of being between -1 and +1. So those are the only input values we can have for the inverse sine. So here, 0.5 is in that interval. Let's say 0.5 is between -1 and +1. So if that's the case, then these will undo each other. This will just be equal to 0.5. In part B, we have something that's outside of that domain. We have the sine of the inverse sine of 1.8. So 1.8 is definitely bigger than 1. It's outside of the domain of the inverse sine. So this statement will just be undefined. We won't be able to get a defined value out of that inner function. So I'll just have to say the sine of the inverse sine of 1.8 is undefined. Let's look at something similar for the inverse cosine. So we'll get some more practice with this. So we're considering the domain and range of these functions. So for the inverse cosine, we said the domain is similar to the inverse sine in between -1 and +1. And the range of the inverse cosine is between 0 and pi. So let's look at our first example. So in part A, we have the inverse cosine of the cosine of pi over 2, or pi over 12. Well, pi over 12, that's definitely in between 0 and pi. It's in the allowable range of the inverse cosine. So these will undo each other, and we can just say this will be equal to pi over 12. So we're just checking that this angle is in the range of the inverse function on the outside. For part B, we have the cosine of the inverse cosine of -0.4. If your inverse function is on the inside, just double check that that angle is in the domain of the inverse trig function. The domain of the inverse cosine is between -1 and 1. And -0.4 is in between those two. So it's in the domain. So we can say the cosine of the inverse cosine of -0.4 is equal to -0.4. Let's look at part C. We have the inverse cosine of the cosine of -2 pi over 3. Now the inverse function is on the outside, so we need to see if -2 pi over 3 is in that restricted range of the inverse function. So where is -2 pi over 3? Positive 2 pi over 3 would be up here in the second quadrant, so the negative angle would be down in the third quadrant, down here. And we said the restricted range of the inverse cosine is between 0 and pi, so we need an equivalent angle on the top half of the unit circle that would have the same cosine value. So that would just be our positive 2 pi over 3. So that means that, let's come back to our original statement, the inverse cosine of the cosine of -2 pi over 3 isn't equal to -2 pi over 3, but rather positive 2 pi over 3. So we had to find that other angle in the reduced range that will give the same cosine value. And then for part D, let's stick it down here, we have the cosine of the inverse cosine of pi. So now the inverse function is inside, so we need to ask, is pi in the domain of the inverse cosine function, which is between -1 and +1? Pi is 3.14, continuing the decimal from there, so definitely greater than 1. So we'll have to say undefined. So these can be a little bit tricky, and these little tables are helpful. This is saying when the inverse trig function is on the outside, for the cosine, they'll undo each other. You'll just get that angle out if x is between 0 and pi, meaning the ultimate output has to be in that restricted range of the inverse cosine. And then if the inverse function is on the inside here, you have to be sure that this input value x is in that restricted domain between -1 and +1. And we could say a similar thing for the tangent. They don't give us some examples to work with, but remember the tangent is restricted between -pi/2 and +pi/2. So we see that here, we'd have to give an angle somewhere in that interval. But the tangent is more forgiving here because remember the domain of the inverse tangent is all real numbers, -infinity to +infinity. So this statement will always be true, that if you take the tangent of an inverse tangent of some value, you'll just get that value as the output. All right, the next section is on finding the inverse function of a trig function that's given where there's been some modifications. So for example, let's look at part A. We want the inverse function of this function 2 times the sine of x minus 1. So general strategy, if you remember, to find an inverse function, given some equation, and we can replace f of x with y. It's usually our starting point. Just swap x and y. So for example, I would stick my x over here, and now y would be inside of the sine function. Oh, and this is -1 out here. So swap x and y, and then resolve for y. So that worked with more algebraic functions. But we can do that also with the trigonometric functions too. So I swapped x for y. Now I want to solve for this y. So first I want to just isolate this trig function, the sine of y. So let's add 1 over to the other side. So give me x plus 1 equals 2 sine of y. Then I'll divide by 2. So x plus 1 over 2 equals the sine of y. And then if I want to solve for y, I want to undo that sine function. Well, I can take the inverse sine of both sides. And that will just give me y over here. So this will be our inverse of that original function they gave us. So again, the trick is to write out the function, swap x and y, and then solve it for y. And in part B, it wants the range of f and the domain and range of f inverse. So let's take a look. So let's remember that restricted domain of the inverse sine. Oops. So for inverse sine of x, the domain was bound between -1 and +1. So we can say something like this. X is in between -1 and +1. But we have something a bit more complicated. We have this statement, the inverse sine of x plus 1 over 2. Well, we can set up a similar inequality here. Just taking what's inside. Here we just took this x and set it in between -1 and +1. So I'll just take what is inside. X plus 1 over 2 should be in between -1 and +1. Oh, and it can be equal to these as well. And then now let's just solve this inequality for x, and that will give us our domain. So I'll multiply everything by 2. This will become -2 is less than or equal to x plus 1 less than or equal to +2. And then I'll subtract 1 from all sides. So -2 minus 1 is -3. And then 2 minus 1 is 1. So x is between -3 and +1 when we're considering this x inside of this inverse sine function. So that will give us our domain. So I can say the domain of this inverse function is in between -3 and 1. And in the range, they gave us this domain from the original statement. That will be the range of our function because we're swapping domains and ranges. So this will be from -π/2 to π/2. So if we just considered the domain of the original inverse sine function, should have been a -1 here. We just placed what was inside of our function in between those same two endpoints and then solved the inequality for x. All right, the last section here has us solve a little trig equation. So we're given 3 times the inverse sine of x equals pi. And it's asking us to solve. So we want to solve for x. We want to get to a point where x is just equal to something. So first, let's isolate this inverse trig function. I'm going to divide both sides by 3. So the inverse sine of x equals pi/3. Now this is like a question we saw earlier. So we can take the sine of both sides. X equals the sine of pi/3. So then what's the sine of pi/3? Pi/3 is up here in the first quadrant. This has the coordinate point 1/2 √3/2. And the sine is the y-coordinate. So that means x is equal to root 3 over 2. So just need to algebraically solve for the inverse trig function. Maybe we have to add or subtract things over to the other side. Just get that alone on one side equal to everything else, and then you can take, in this case, the sine of both sides. That will undo the inverse trig function, and then here we just had to evaluate the sine of pi over 3. So this is a very light introduction to solving trig equations, which we'll see in a later video. Okay, that's it for this section. Let's come back up to the description. So we defined the inverse sine, found some values with the inverse sine. The same thing for the cosine and the tangent. So we defined those inverse trig functions. There is that kind of tricky section of using properties of the inverse functions to find exact values of composite functions. That's like when we had an inverse trig function of the original, or say like the sine of the inverse sine of x. We had to be really careful about our restricted domain and range in that case. Then we found the inverse function of a trigonometric function, and then we just ended solving a small equation involving an inverse trig function. All right, that's it for this video. Next time we will look at the secant, cosecant, and cotangent and solve some more complex composite functions. All right, I'll see you then.